What if I told you that our sun, pause, might not be alone? Picture this while you're going about your daily life, completely unaware, there could be something lurking in the darkness beyond our solar system. Something that has been silently orchestrating the greatest catastrophes in Earth's history for millions of years. Something that could be approaching us right now. This isn't science fiction. This is the Nemesis hypothesis. And it's one of the most chilling theories in modern astronomy. You see, roughly every 26 million years, something extraordinary happens to life on Earth. Not extraordinary in a good way. Extraordinary in a wipe out nearly everything that's alive kind of way. The pattern is so precise, so clockwork-like, that it can't possibly be a coincidence. So what's causing it? What kind of cosmic force operates with such deadly regularity? The answer might be hiding in plain sight, and it might be coming for us next. Let's start with what we know for certain. Earth has experienced 5 major mass extinction events that we can clearly identify in the geological record. These weren't gradual die-offs or slow environmental changes. These were catastrophic events that fundamentally reset life on our planet. The most famous, of course, is the one that killed the dinosaurs 66 million years ago. But here's what's truly unsettling. That was actually one of the smaller extinction events. Worse was something called the end Permian extinction, which occurred about 252 million years ago. This event was so devastating that paleontologists call it the Great Dying. Imagine this. 96% of all marine species gone. 70% of all land vertebrates extinct. The Earth's oceans became acidic wastelands, and the atmosphere filled with toxic gases. It was the closest life on Earth has ever come to complete annihilation. And yet, somehow, life survived and eventually flourished again. But here's where things get really interesting. In 1984, a paleontologist named David Ropp was studying these extinction events when he noticed something that made his blood run cold. The timing wasn't random. These massive die-offs were occurring in a cycle, roughly every 26 million years, like clockwork. Now, Ropp wasn't some fringe theorist. He was a respected scientist at the University of Chicago, and he approached this discovery with the skepticism of a trained researcher. But the more data he analyzed, the more undeniable the pattern became. The statistical probability of this being a coincidence? Essentially 0. Think about what this means. For something to cause such regular devastation over hundreds of millions of years, it has to be something incredibly powerful and incredibly predictable. Geological processes don't work this way. Volcanic eruptions, climate changes, even asteroid impacts from the asteroid belt. None of these follow such a precise schedule. So what could be powerful enough to repeatedly trigger mass extinctions with clockwork precision? Ropp and his colleagues began to consider possibilities that seemed almost too strange to believe. The first theory they explored was orbital mechanics. Could Earth's orbit around the sun be changing in a regular cycle, periodically exposing us to cosmic radiation or asteroid bombardments? But Earth's orbit is remarkably stable. The gravitational dance between Earth and the Sun doesn't operate on 26 million year cycles. What about our solar system's movement through the galaxy? Our entire solar system orbits around the center of the Milky Way, taking about 225 million years to complete one galactic year. During this journey, we periodically pass through the galaxy's spiral arms, where there's more cosmic radiation and a higher density of stars. But again, the timing doesn't match the extinction cycle. Then someone proposed something that changed everything. What if our sun isn't the lone star we've always believed it to be? What if it has a companion? Now, this might sound impossible. After all, wouldn't we have noticed another star in our solar system by now? But here's the thing. Roughly half of all stars in our galaxy exist in binary systems. Two stars locked in a gravitational dance, orbiting around their common center of mass. It's actually more common for stars to have companions than to exist alone. And here's where it gets really interesting. If our sun had a stellar companion, it wouldn't necessarily have to be visible to the naked eye. It could be what astronomers call a brown dwarf, essentially a failed star. These objects are incredibly dim, emitting very little visible light. Or it could be a red dwarf star, small and cool, barely glowing in the cosmic darkness. This hypothetical companion was given a name that perfectly captures its ominous nature: Nemesis, named after the Greek goddess of vengeance. This dark star could be lurking somewhere in the outer reaches of our solar system, following a highly elliptical orbit that brings it close enough to wreak havoc every 26 million years. But how would such a stellar companion cause mass extinctions? The answer lies in something called the Oort cloud. A vast spherical shell of icy objects that surrounds our solar system at a distance of nearly a light year from the sun. This cloud contains trillions of comets, just sitting there in the cold darkness, waiting. When Nemesis approaches the outer edge of our solar system during its long, elliptical orbit, its gravitational influence would destabilize the Oort cloud. Thousands, perhaps millions of comets would be knocked out of their stable orbits and sent hurtling toward the inner solar system. The result? A cosmic bombardment lasting millions of years. Exactly what we see in the geological record during extinction events. The beauty of this theory is its elegance. One mechanism, one dark companion star, could explain the regular timing of mass extinctions. The evidence of increased impact rates during extinction periods, and the sheer scale of devastation required to reset life on Earth. But here's what should keep you awake at night. If Nemesis exists, if this pattern is real and continuing. When is the next extinction event due? The last major extinction event occurred about 11 million years ago. If the cycle continues, we could be approaching another period of cosmic bombardment. In fact, some scientists suggest we might already be in the early stages. Increased comet activity, subtle changes in the outer solar system. Could these be the first signs that Nemesis is beginning its return journey toward us? The implications are staggering. If Nemesis is real, then everything we think we know about our place in the cosmos needs to be reconsidered. We're not just inhabitants of a peaceful solar system orbiting a solitary star. We're potential victims of a cosmic cycle that has been playing out for hundreds of millions of years. But here's the thing that makes this more than just an academic exercise. Unlike the dinosaurs, unlike every other species that has faced this cosmic clockwork of destruction, we know it might be coming. We have the technology to search for Nemesis, to track its approach, and maybe, just maybe, to do something about it. The question is, are we looking in the right places? And more importantly, do we have enough time? The hunt for Nemesis has become one of the most important searches in human history, because finding our dark companion isn't just about satisfying scientific curiosity, it's about survival itself. But searching for Nemesis is like trying to find a single black cat in a coal mine at midnight. We're looking for an object that might be incredibly dim, incredibly distant, and moving through space on an orbit that could take it as far as 3 light years from the sun. To put that in perspective, the nearest star to our solar system, Proxima Centauri, is only 4.2 light years away. When astronomers first began seriously searching for Nemesis in the 1980s, they faced seemingly impossible odds. The technology of the time was limited to ground-based telescopes that could only detect relatively bright objects. If Nemesis was a brown dwarf or a very dim red dwarf star, it might be virtually invisible to these instruments, but scientists are nothing if not resourceful. If they couldn't see Nemesis directly, maybe they could detect its gravitational fingerprints. This is where the detective work really began. Think of it like investigating a crime scene. You might not be able to see the perpetrator, but you can look for evidence of their presence. In this case, that evidence would be the disturbed orbits of objects in the outer solar system. Particular long-period comets. Long-period comets are fascinating objects. These are comets that take hundreds or thousands of years to complete a single orbit around the sun. They spend most of their time in the frigid outer reaches of our solar system, far beyond the orbit of Pluto. When something gravitationally disturbs them, they come screaming in toward the sun, creating the spectacular comet displays we occasionally see in our night sky. Here's the thing about these comets. Their orbits should be randomly distributed if they're only being influenced by the sun and the known planets. But if there's a massive object like Nemesis periodically passing through the outer solar system, it would create patterns in these comet orbits. Clusters of comets coming from particular directions or arriving at particular times. Astronomers began meticulously cataloging and analyzing the orbits of every long-period comet they could find. They looked for statistical anomalies, clustering patterns, anything that might indicate the gravitational influence of an unseen stellar companion. The results were tantalizing but inconclusive. Some studies seem to show clustering in comet orbits that could be consistent with Nemesis. Others found no such patterns. The problem was that the sample size was relatively small, and comet orbits can be influenced by many factors. including the gravitational effects of passing stars and giant molecular clouds in our galaxy. The technology was advancing rapidly. In the 1990s and 2000s, a new generation of infrared space telescopes opened up entirely new possibilities for the Nemesis search. Brown dwarfs, while dim and visible light, are actually quite bright in infrared radiation. They're still warm from their formation, glowing with heat in the infrared spectrum. The most important of these missions was the Wide Field Infrared Survey Explorer, or WISE. Launched in 2009, WISE mapped the entire sky in infrared light with unprecedented sensitivity. If there was a brown dwarf within a few light years of our solar system, WISE should have been able to detect it. The astronomy community held its breath as WISE data was analyzed. This was it, the moment of truth. If Nemesis existed as a brown dwarf companion to our sun, WISE would find it. The results were both disappointing and reassuring. WISE found no evidence of a brown dwarf companion within about 10,000 astronomical units of the sun. An astronomical unit is the distance from Earth to the sun. So we're talking about a sphere with a radius 10,000 times the Earth-Sun distance, but still well within the range where Nemesis could exist and influence the Oort cloud. But here's where things get really interesting. The absence of evidence isn't necessarily evidence of absence. WISE ruled out brown dwarf companions, but what about other possibilities? Nemesis could be a very low-mass red dwarf star, so dim that even WIS, it couldn't detect it at interstellar distances. Or it could be something even more exotic. A primordial black hole, a massive planet ejected from another star system, or even a dense cloud of dark matter dot. The search expanded beyond traditional astronomical surveys. Scientists began looking at the subtle gravitational effects that Nemesis might have on the orbits of planets in our solar system. If there's a massive object in the outer solar system, it should cause tiny perturbations in planetary orbits that could be detected with precise measurements. This is incredibly delicate work. We're talking about detecting orbital changes that might be smaller than the width of a human hair when scaled to planetary distances. But modern astronomical techniques are capable of this level of precision. NASA's Jet Propulsion Laboratory maintains incredibly accurate models of planetary motion. These models track the positions of planets to within a few kilometers, accounting for all known gravitational influences. Any unexplained deviations from these models could indicate the presence of an unknown massive object dot so far. No such deviations have been conclusively detected, but the search continues with ever-increasing precision. New space missions like the European Space Agency's Gaia satellite are mapping the positions and motions of billions of stars with unprecedented accuracy. If Nemesis is out there, its gravitational influence on nearby stars might eventually give it away. There's another intriguing possibility that's emerged from recent research. What if Nemesis isn't a star at all, but rather a massive planet? A super-Earth, or even a gas giant that was somehow ejected from the inner solar system billions of years ago? Computer simulations of early solar system evolution suggest that planetary systems can be quite chaotic. During their formation, planets can migrate, collide, or even get ejected entirely. If our solar system once had an additional massive planet that was ejected into a distant eccentric orbit, it could potentially explain the extinction cycle without requiring a stellar companion. This idea gained credibility with the discovery of what astronomers call Planet 9, a hypothetical massive planet that might exist in the outer solar system far beyond Neptune. While Planet 9, if it exists, probably isn't Nemesis. The fact that there might be unknown massive objects in our outer solar system keeps the Nemesis hypothesis alive. But here's what's really keeping astronomers up at night. All of these searches have been based on the assumption that we know what we're looking for. What if Nemesis is something completely unexpected? What if it's a type of object that we haven't even theorized yet? The universe has a habit of surprising us. Black holes were theoretical curiosities until we found them. Dark matter and dark energy make up most of the universe, but we still don't know what they actually are. Neutron stars seemed impossible until we detected their radio pulses. What if Nemesis is our next cosmic surprise? An object or phenomenon that challenges our current understanding of astrophysics. The search continues with new urgency as we develop more sophisticated detection methods. Ground-based surveys like the Large Synoptic Survey Telescope, now known as the Vera Rubin Observatory, will soon begin mapping the entire visible sky every few nights, looking for any objects that move or change brightness. Space-based missions are being planned that will extend our search capabilities even further. The James Webb Space Telescope, with its incredible infrared sensitivity, might be able to detect brown dwarfs that were too dim for previous surveys. But even as we search for Nemesis itself, the evidence for its effects continues to mount. The geological record of Earth reads like a cosmic crime scene, and the more we examine it, the more disturbing the pattern becomes. Let's approach this like forensic investigators. We have a series of catastrophic events spanning hundreds of millions of years, each leaving distinctive evidence in Earth's rock layers. The question is, what connects these events? What signature ties them together? The first major clue came from the discovery of the iridium layer at the Cretaceous-Paleogene boundary, the rock layer that marks the extinction of the dinosaurs. Iridium is incredibly rare in Earth's crust, but it's relatively common in asteroids and comets. The presence of this iridium-rich layer worldwide suggested that a massive extraterrestrial impact occurred exactly at the time of the dinosaur extinction. This was revolutionary. For the first time, scientists had physical evidence linking a mass extinction to a cosmic impact. But was this a one-time event or part of a larger pattern? Researchers began examining rock layers corresponding to other extinction events, looking for similar evidence of extraterrestrial impacts. What they found was both fascinating and terrifying. The end Permian extinction, the Great Dying that wiped out 96% of marine life, shows evidence of multiple impacts occurring over a relatively short geological time period. Not just one asteroid, but a series of impacts that pummeled Earth repeatedly. The late Devonian extinction, which occurred about 375 million years ago, also shows signs of impact events. Shocked quartz crystals, tiny glass spherules called microtectites, elevated levels of extraterrestrial elements, all the signatures of cosmic bombardment. But here's where it gets really interesting. These aren't isolated impact events. They appear to be part of what astronomers call comet showers, periods lasting millions of years during which Earth experiences dramatically increased rates of cosmic bombardment. Think about what this means. Instead of random asteroid impacts occurring occasionally over geological time, we're seeing evidence of coordinated assault periods when dozens or hundreds of objects rain down on Earth over relatively short time spans. Is exactly what the Nemesis hypothesis predicts. As our hypothetical stellar companion approaches the outer solar system on its 26 million year orbit, it would gravitationally disturb the Oort cloud, sending waves of comets toward the inner solar system. Some of these comets would impact Earth, creating the comet shower signature we see in the geological record. But the evidence goes beyond just impact signatures. Scientists have also discovered that many extinction events are associated with massive volcanic eruptions, what geologists call large igneous provinces or flood basalts. The end Permian extinction coincided with the eruption of the Siberian traps. A volcanic event so massive that it covered an area larger than Europe with lava up to several kilometers thick. The end Cretaceous extinction, which killed the dinosaurs, occurred at the same time as the eruption of the Deccan traps in what is now India. At first glance, this might seem to contradict the impact theory. If volcanic eruptions are causing these extinctions, why do we need to invoke cosmic bombardment? But here's the really chilling possibility. The impacts themselves might be triggering the volcanic eruptions. Earth's crust is like a thin shell floating on a sea of molten rock. It's already under enormous pressure from the heat and movement of the mantle below. A massive impact, or series of impacts, could be like hitting the shell with a hammer, cracking it and allowing molten rock to pour through. Computer simulations of large impacts suggest that the shock waves from a major asteroid or comet strike can travel completely through the Earth, potentially triggering volcanic eruptions on the opposite side of the planet. If Earth is being bombarded by multiple large objects during a comet shower, the cumulative effect could destabilize volcanic systems worldwide. This creates a terrifying feedback loop. Cosmic bombardment triggers massive volcanic eruptions, which release enormous amounts of ash and toxic gases into the atmosphere. The combination of impact winters from asteroid strikes and volcanic winters from eruptions could plunge Earth into prolonged periods of environmental chaos. But let's examine the timing more closely, because this is where the Nemesis hypothesis becomes either compelling or falls apart entirely. David Ropp's original analysis suggested a 26 million year cycle in extinction events. But as more data has become available, scientists have refined this estimate. Some studies suggest the cycle might be closer to 27 or 28 million years. Others question whether the cycle is truly periodic or whether it's just a statistical coincidence. This is where the detective work becomes incredibly sophisticated. Scientists are now using advanced statistical techniques to analyze not just the timing of extinction events, but also the timing of crater formation on Earth, the ages of impact glass found in geological layers, and even the orbits of asteroids in the inner solar system. One of the most compelling pieces of evidence comes from studies of terrestrial impact craters. Earth has been hit by large asteroids and comets throughout its history, and while most of the craters have been erased by erosion and plate tectonics, we can still identify and date many of them. When scientists plotted the ages of known impact craters over the past 250 million years, they found something remarkable. The impacts aren't randomly distributed in time. They show clustering periods when Earth experienced significantly more large impacts than average dot, and here's the kicker dot dot. These periods of increased cratering correspond closely to the timing of mass extinction events. It's as if Earth periodically enters a cosmic shooting gallery, experiencing waves of bombardment that coincide with biological catastrophes, but the evidence extends beyond just Earth. Scientists have also examined impact craters on the Moon, which preserves a much more complete record of bombardment because it has no atmosphere or geological activity to erase craters. Lunar crater studies reveal something fascinating. The Moon also shows evidence of periodic increases in impact rates. Since the Moon orbits Earth, it would be subject to the same comet showers that affect our planet. The fact that both Earth and the Moon show similar patterns of periodic bombardment strengthens the case for an external cause. Something like Nemesis Star. Now, let's talk about the most disturbing aspect of this research. If the 26 million year extinction cycle is real and continuing dot dot, when is the next one due? The last major extinction event occurred during the Miocene epoch about 11 million years ago. This event wiped out many marine species and contributed to significant climate changes that affected terrestrial ecosystems worldwide. If we're still on the 26 million year cycle, that means we're approaching the midpoint between extinction events. But here's what should concern us, dot, dot, dot. Some scientists argue that we might already be experiencing the early stages of the next extinction period, dot, the current geological epoch, which began about 11,700 years ago, is called the Holocene. But many geologists now argue that we've entered a new epoch, the Anthropocene, defined by human impact on global ecosystems. And this human-driven environmental change might be masking or even accelerating natural extinction cycles. Current extinction rates are already elevated, far above natural background levels due to human activities. If we're simultaneously entering a period of cosmic bombardment, if Nemesis is beginning its approach toward the outer solar system, the combined effects could be catastrophic beyond imagination, but there's another possibility that's even more chilling. What if the cycle has already been disrupted? What if human space activities, climate change, or other factors have altered the delicate gravitational balance that governs these cosmic cycles? Some researchers have noted increased comet activity in recent decades. Long-period comets seem to be arriving slightly more frequently than historical averages suggest. Could this be statistical noise? Or could it be the first sign that something is stirring in the outer solar system? The challenge is that cosmic processes operate on timescales that dwarf human civilization. A sudden increase in comet activity might unfold over thousands of years. From our perspective, it would seem gradual and natural. We might not recognize the pattern until it's too late to do anything about it. This is why understanding the Nemesis cycle isn't just an academic exercise. If we can identify the pattern, if we can predict when the next bombardment period will begin, we might have time to prepare. Time to develop technologies to deflect incoming objects, to build shelters, to preserve human civilization and knowledge. But if we're wrong about the timing, if the cycle has been disrupted, or if we've misunderstood the pattern entirely, we could be caught completely unprepared for a cosmic catastrophe that has been building for millions of years. So what would it actually look like? What would happen if Nemesis triggered a new extinction event today in our modern interconnected world? Unlike the dinosaurs, we wouldn't be caught completely by surprise. Our astronomical surveys would begin detecting anomalies years, possibly decades before the main bombardment began. But this advance warning might be both a blessing and a curse. Picture this scenario. It's 2045, and a large synoptic survey telescope has been operational for several years, mapping the entire sky every few nights with unprecedented precision. Automated algorithms analyze millions of observations daily, looking for anything that moves, changes, or appears where nothing was before. At first, it's just statistical noise. A few more long-period comets than usual. Nothing alarming. Comet populations naturally fluctuate, but as months pass, the pattern becomes undeniable. Comets are arriving from a particular region of the sky at a rate far above normal. Something has disturbed the Oort cloud. The astronomical community mobilizes. Every major telescope on Earth and in space turns toward the outer solar system. What they discover sends shock waves through the scientific world. Not just a few dozen comets, but hundreds, possibly thousands of objects, all on trajectories that will bring them into the inner solar system over the next several decades. The first public announcement is carefully worded. Increased comet activity detected. No immediate threat to Earth. Continued monitoring planned. But behind closed doors, scientists are running calculations that keep them awake at night. Based on the trajectories and sizes of detected objects. Statistical models predict that dozens of comets larger than 1 kilometer in diameter will pass through the inner solar system over the next 50 years. The probability of at least one Earth impact during this period? Nearly certain, but the real horror begins when they detect the source of the disturbance. Deep in the outer solar system, moving on a highly elliptical orbit, is an object unlike anything in our astronomical catalogs. It's too small to be a star, too large to be a planet, and it's been invisible to our surveys because it emits almost no light. Nemesis. After decades of searching, humanity finally finds its dark companion. Just as it begins to unleash hell upon the inner solar system, the initial public reaction is disbelief, then panic, then a strange kind of numbness. How do you process the information that your species is about to face the same cosmic catastrophe that wiped out the dinosaurs? How do governments respond to a threat that operates on geological timescales but requires immediate action? The first impacts would likely be smaller objects, house-sized asteroids that burn up in Earth's atmosphere or create localized damage if they reach the ground. Each one would be a reminder of what's coming. Each impact would be tracked obsessively by news media, analyzed by experts, and feared by populations worldwide. But it's the psychological impact that might be most devastating. Unlike natural disasters that strike without warning, this catastrophe would unfold with agonizing slowness. Humanity would watch its doom approaching for years, tracking every object, calculating every trajectory, knowing that some of these cosmic bullets have Earth's name on them. The first truly catastrophic impact might be a comet about 2 kilometers in diameter, large enough to cause regional devastation, but small enough that civilization might survive. Let's say it hits the Pacific Ocean, roughly halfway between Hawaii and Japan. The initial impact creates a fireball visible from space, vaporizing billions of tons of seawater and ocean floor. The explosion is equivalent to roughly 100,000 megatons of TNT. Several times more powerful than all the nuclear weapons on Earth combined. Within minutes. Tsunami waves hundreds of meters high race outward from the impact site at jet aircraft speeds. Tokyo, Sydney, Los Angeles, Seattle. Coastal cities around the Pacific Rim have perhaps 6 to 8 hours of warning. Mass evacuations begin, but moving millions of people is a process that takes days, not hours. The tsunamis that follow make the 2004 Indian Ocean tsunami look like a small wave. Walls of water carrying millions of tons of debris surge hundreds of kilometers inland, obliterating everything in their path. Entire metropolitan areas disappear beneath the waves, but the tsunamis are just the beginning. The impact throws enormous amounts of material into the atmosphere. Vaporized rock, seawater, and debris that blocks sunlight and begins to spread around the globe. Within weeks, global temperatures begin to drop as the planet enters what scientists call an impact winter. Modern agriculture, dependent on stable weather patterns and consistent growing seasons, begins to collapse. Supply chains that span continents break down as transportation networks are disrupted by both the direct effects of the impact and the secondary effects of climate disruption, and this is just the first impact. Astronomical surveys are now tracking hundreds of additional objects, some even larger than the first. The bombardment that has begun will continue for decades, possibly centuries. The second major impact occurs just 18 months later. This one is larger, a 5-kilometer comet that strikes the Atlantic Ocean east of the Azores. The explosion is visible from space stations as a brief second sun. The impact creates a crater on the ocean floor larger than Rhode Island and triggers seismic activity that can be measured worldwide. Cumulative effects are now becoming impossible to ignore. 2 major impacts have filled the atmosphere with so much debris that global temperatures have dropped by an average of 5 degrees Celsius. The growing seasons in major agricultural regions have been shortened by weeks or months. Crop yields collapse worldwide, but it's not just the direct physical effects that threaten human civilization. Our modern world is incredibly interconnected and therefore incredibly fragile. Supply chains depend on just-in-time delivery. Financial systems depend on global communications networks. Food production depends on fertilizers and equipment manufactured thousands of kilometers from where crops are grown. As impact winters disrupt growing seasons and tsunami damage destroys coastal infrastructure, the complex web of modern civilization begins to unravel. Port cities that handle most of the world's shipping are repeatedly damaged by impacts and their secondary effects. Manufacturing centers are disrupted by climate changes that affect everything from power generation to worker populations. The social and political consequences are equally catastrophic. Mass migrations begin as coastal populations flee repeatedly devastated areas. Food shortages lead to social unrest and conflict between nations. Economic systems collapse as the physical infrastructure they depend on is repeatedly destroyed. Perhaps most tragically, the extended timescale of the bombardment prevents recovery. In previous mass extinctions, ecosystems could begin recovering once the main catastrophic period ended. But with objects continuing to impact Earth for decades or centuries, there's no opportunity for environmental or social systems to stabilize. The third major impact is perhaps the most devastating, not because it's larger than the previous ones, but because it strikes at a moment when human civilization is already severely weakened. A 4-kilometer comet impacts the North American continent, creating a fireball that incinerates everything within a radius of several hundred kilometers. Shockwave levels forests and cities across half the continent. The heat pulse ignites wildfires that burn uncontrolled for months. But perhaps most significantly, the impact occurs near the Yellowstone volcanic system, and the massive shock triggers the supervolcanic eruption that scientists have long feared. Now, Earth faces not just cosmic bombardment, but massive volcanic activity as well. The Yellowstone eruption alone ejects more ash and toxic gases into the atmosphere than all human industrial activity in history. Combined with the debris from multiple impacts, the atmosphere becomes so choked with particles that very little sunlight reaches the surface. This is the feedback loop that may have driven previous mass extinctions. Cosmic bombardment triggers volcanic activity, creating a combined impact volcanic winter that can last for decades. Surface temperatures drop below freezing even in tropical regions. Photosynthesis essentially stops as plants cannot survive in the perpetual twilight. At this point, The collapse of human civilization is essentially complete. The survivors, perhaps a few 100 million people out of Earth's current population of 8 billion, are scattered in small groups, struggling to survive in a world that has become almost alien, but the bombardment continues. Smaller impacts occur every few months, larger ones every few years. Each one resets any progress toward recovery, adding more debris to the atmosphere, triggering more seismic activity, making the planetary environment even more hostile to life. This is what extinction looks like for an intelligent species. Not a single catastrophic moment, but a prolonged collapse spanning decades or centuries. Unlike the dinosaurs, humans would be painfully aware of what was happening to them. They would understand the cosmic forces involved, track the incoming objects, and know with scientific precision exactly how their species was being eliminated. The question that haunts this scenario is whether human intelligence and technology would be enough to make a difference. Could we deflect some of the incoming objects? Could we build shelters capable of protecting significant populations? Could we preserve enough knowledge and genetic diversity to allow the species to recover once the bombardment finally ended? Or would we, like so many species before us, simply become another layer in Earth's geological record? Evidence of a world that once supported complex life before the dark star returned to bring death from the sky. Target length 1,500 words, but we're not the dinosaurs. We're not helpless creatures waiting for cosmic catastrophe to claim us. For the first time in Earth's history, a species has developed the knowledge and potentially the technology to fight back against extinction. The question is, what would that fight look like? The first line of defense would be early detection and deflection. Unlike previous extinction events, we wouldn't face complete surprise. Our astronomical surveys would give us decades, possibly centuries, of advance warning before the main bombardment began. This time advantage could be crucial. Asteroid and comet deflection isn't science fiction. It's engineering. We already have the basic technologies needed to alter the trajectory of incoming objects. The challenge is scaling these technologies up to handle not just one or two threats, but hundreds or thousands of objects over an extended period. For smaller objects, anything under a few 100 meters in diameter, we could potentially use kinetic impactors. These are essentially high-speed projectiles that slam into the target object, changing its velocity just enough to make it miss Earth. European Space Agency's DART mission successfully demonstrated this technique by altering the orbit of the asteroid Dimorphos in 2022. But kinetic impactors require precise timing and considerable advance warning to be effective. Changing an object's trajectory by even a tiny amount can cause it to miss Earth entirely, but only if you apply that change years or decades before the predicted impact. For larger objects, the multi-kilometer comets that could cause global catastrophes, we would need more powerful methods. Nuclear deflection might be our only option, not nuclear destruction, which could create multiple smaller but still dangerous fragments, but nuclear deflection. using nuclear explosions to vaporize part of the object's surface and create a natural rocket effect. This technique, sometimes called nuclear pulse propulsion, has been studied extensively by space agencies. The challenge isn't the physics. We understand how it would work. The challenge is building and deploying dozens or hundreds of nuclear-equipped spacecraft on relatively short notice, but deflection alone might not be enough. If Nemesis triggers a bombardment period lasting decades or centuries, we couldn't possibly deflect every dangerous object. Some impacts would be inevitable. Humanity would need to prepare for survival in a world undergoing repeated cosmic bombardment. This is where the concept of deep shelters becomes critical. Not simple fallout shelters designed to protect against nuclear war, but massive underground cities capable of sustaining large populations for extended periods, possibly centuries. These wouldn't be cramped bunkers, but sophisticated ecosystems. Vast underground chambers with artificial lighting for agriculture. Closed-loop life support systems that recycle air, water, and waste with near-perfect efficiency. Manufacturing facilities capable of producing everything from medical supplies to electronic components. The technical challenges are immense but not insurmountable. The technology for closed-loop life support already exists on a small scale aboard the International Space Station. Hydroponic agriculture can produce food in controlled environments without soil or natural sunlight. Geothermal energy could provide power for centuries, but the real challenges might be psychological and social. How do you maintain human civilization in underground chambers for decades or centuries? How do you prevent social collapse, maintain genetic diversity, preserve knowledge and culture? Historical examples aren't encouraging. Isolated human populations tend to develop serious problems over time. Genetic bottlenecks, social stratification, loss of technological knowledge. Building sustainable underground civilizations would require careful planning of everything from governance structures to breeding programs. There's another possibility that's both more ambitious and potentially more effective: space-based survival. If Earth's surface becomes uninhabitable due to cosmic bombardment, humanity could potentially survive in space colonies or on other worlds. Mars represents the most obvious refuge. The red planet is far enough from Earth that it wouldn't be directly affected by bombardment of the inner solar system. Mars has resources that could support human colonies: water ice, carbon dioxide, minerals for construction and manufacturing. But establishing Mars colonies capable of supporting significant populations would require massive technological advances. Current space technology can barely maintain a few dozen people on the International Space Station. Supporting millions of refugees on Mars would require completely new approaches to space transportation, life support, and resource utilization. The moon might be more accessible but less sustainable. Lunar colonies could be established more quickly and cheaply than Mars settlements, but the moon lacks many of the resources needed for long-term survival. There's water ice at the lunar poles, but no atmosphere, no magnetic field to protect against radiation, and limited raw materials for manufacturing. Perhaps the most ambitious option would be massive space habitats. Artificial worlds built from asteroid materials and powered by solar energy. These could potentially house millions of people in Earth-like environments, completely independent of planetary surfaces. The concept isn't new. Physicist Gerard O'Neill designed detailed plans for space colonies in the 1970s. Modern versions might use rotating cylinders or spheres to create artificial gravity, with forests, lakes, and cities inside. The raw materials exist in our solar system's asteroid belt, enough to build thousands of such habitats. But we're talking about engineering projects that would dwarf anything humanity has ever attempted. The construction of space habitats capable of housing significant populations would require space-based manufacturing, asteroid mining, and transportation systems orders of magnitude beyond current capabilities. There's an even more radical possibility: breaking the cycle entirely. If we could detect Nemesis early enough, we might be able to alter its orbit or even destroy it completely. This would be cosmic engineering on an unprecedented scale, but it might be the only way to permanently end the threat of periodic mass extinctions. Altering the orbit of a stellar companion would require enormous amounts of energy. Perhaps more than human civilization currently produces. We might need to harness the energy output of the sun itself, using technologies like Dyson spheres or stellar engines that are currently pure speculation. Destroying Nemesis completely might be even more challenging. If it's a brown dwarf or a red dwarf star, it could have a mass dozens of times greater than Jupiter. The energy required to disrupt such an object would be comparable to stellar explosions. But here's an interesting possibility. We might not need to destroy Nemesis completely. We might only need to alter its orbit enough to break the 26 million year cycle. Even a small change in its trajectory could shift its closest approach to the solar system, reducing its gravitational influence on the Oort cloud. The technology for such cosmic engineering doesn't exist yet, but the principles are understood. Gravity tractors could slowly alter Nemesis's orbit over millions of years. Massive solar sails could use the pressure of starlight to change its trajectory. Nuclear pulse propulsion could provide the enormous thrust needed to move stellar mass objects. Of course, all of these solutions assume we have enough advance warning to implement them. If Nemesis is already approaching the outer solar system and we only detect it when the bombardment begins, our options become much more limited. This is why the search for Nemesis is so critical. Every year we fail to find it is a year less preparation time if it actually exists. Every improvement in our detection capabilities brings us closer to answering the fundamental question: are we alone in our solar system, or do we have a dark companion that periodically brings death from the sky? But there's another aspect to consider. Preparing for Nemesis-level extinction events would also prepare humanity for other existential threats. The same technologies that could protect us from cosmic bombardment could also defend against supervolcanic eruptions, gamma-ray bursts, rogue planets, or artificial threats of our own making. In a sense, the Nemesis hypothesis is forcing us to mature as a species, to think beyond our home planet, to develop technologies capable of protecting and preserving human civilization against cosmic scale threats. Whether Nemesis exists or not, this maturation process might be essential for our long-term survival in a universe full of dangers we're only beginning to understand. 6 Beyond the Darkness target. Length 1,500 words. So where does this leave us? After decades of searching, analyzing, and theorizing ... what do we actually know about Nemesis? The honest answer is both everything and nothing. We understand the theoretical framework perfectly. We know how a stellar companion could trigger periodic mass extinctions. We can see the evidence in Earth's geological record. We can model the orbital mechanics and predict the consequences, but Nemesis itself remains elusive. Despite increasingly sophisticated astronomical surveys, we haven't definitively detected our hypothetical dark companion. This absence of evidence has forced scientists to reconsider their assumptions and explore alternative explanations. Recent studies have cast doubt on the original 26 million year extinction cycle. Some researchers argue that the pattern isn't as regular as initially believed, or that it could be explained by other cosmic phenomena. Galactic dynamics, encounters with molecular clouds, or oscillations through the galactic plane might account for some of the observed patterns without requiring a stellar companion. But here's what's fascinating about the Nemesis hypothesis. Even if it's wrong, it has revolutionized our understanding of cosmic catastrophes and their role in shaping life on Earth. The search for Nemesis has led to breakthroughs in asteroid detection, impact modeling, and our understanding of how cosmic events influence biological evolution. We now know that extinction events aren't just random bad luck. They're integral parts of evolutionary history, creating the environmental pressures that drive biological innovation and complexity. Without periodic extinctions, life on Earth might never have evolved beyond simple microorganisms. Think about it this way. If the Cambrian explosion hadn't been preceded by major extinction events that cleared ecological niches, complex multicellular life might never have developed. If the extinction that ended the Permian period hadn't opened new evolutionary pathways, dinosaurs might never have evolved. If the asteroid impact hadn't eliminated the dinosaurs, mammals might never have diversified into the incredible variety of species we see today. Including humans. In this sense, extinction events aren't just destructive forces. They're creative forces. They reset the evolutionary game, allowing new forms of life to experiment with different strategies for survival and reproduction. Without periodic catastrophes, evolution might stagnate. This raises profound philosophical questions about our place in the cosmos. If periodic extinctions are necessary for the evolution of intelligence, then the same cosmic cycles that threaten humanity might be responsible for creating humanity in the first place. Are we the accidental products of stellar violence? Did the gravitational dance of binary stars create the environmental conditions necessary for intelligence to emerge? And if so, what does this mean for life elsewhere in the galaxy? The implications extend far beyond our solar system. if stellar companions are common throughout the galaxy, and if they regularly trigger extinction events on planets orbiting those stars, then the cosmos might be full of worlds experiencing periodic biological resets. This could explain one of the greatest mysteries in astronomy, the Fermi paradox. If the galaxy should be teeming with intelligent civilizations, why haven't we encountered any of them? Perhaps because intelligence repeatedly evolves, reaches a certain level of complexity, and then gets wiped out by cosmic catastrophes before it can spread to other star systems. But there's a more optimistic possibility. What if surviving extinction events is the ultimate test of intelligence? What if species that develop the technology to detect and defend against cosmic catastrophes represent a new phase of evolution? The transition from passive victims of cosmic forces to active participants in cosmic processes. This might be where humanity stands today. We're potentially the first species in Earth's history that could survive a Nemesis-triggered extinction event. Not just survive as scattered individuals, but preserve our technological civilization and continue advancing as a species. The search for Nemesis has already driven technological advances that extend far beyond astronomy. Deep space detection systems developed to search for dim stellar companions have applications in surveillance, navigation, and communication. Impact modeling software helps us understand not just cosmic catastrophes, but also volcanic eruptions, tsunami propagation, and climate change effects. Space-based survival technologies developed to prepare for extinction events could enable permanent human presence throughout the solar system. Closed-loop life support systems, asteroid mining, and large-scale space construction could transform humanity from a single planet species to a spacefaring civilization. Perhaps most importantly, the Nemesis hypothesis has changed how we think about risk and planning. For the first time in human history, we're seriously considering threats that operate on geological timescales and developing strategies to counter them. This long-term thinking has applications beyond cosmic catastrophes. Climate change, resource depletion, technological risks. All of these challenges require the same kind of multi-generational planning and technological development that Nemesis preparation would demand. But let's return to the central question. Does Nemesis actually exist? The latest astronomical surveys have ruled out many possibilities, but they haven't eliminated the hypothesis entirely. Brown dwarf companions bright enough to detect with current technology don't seem to exist in our solar system. But dimmer objects, very low-mass red dwarfs, massive planets, or exotic objects we haven't thought of yet, could still be lurking in the outer darkness. The next generation of astronomical instruments might finally answer the question definitively. The James Webb Space Telescope, with its unprecedented infrared sensitivity, could detect brown dwarfs too dim for previous surveys. The Large Synoptic Survey Telescope will map the positions and motions of billions of objects, potentially revealing the gravitational influence of unseen companions. But even if these surveys fail to find Nemesis, the search will have been worthwhile. We'll have mapped our cosmic neighborhood with unprecedented precision, developed technologies for detecting and deflecting dangerous objects, and prepared our species for threats we can't even imagine yet. In a sense, the Nemesis hypothesis represents humanity's coming of age as a cosmic species. For billions of years, life on Earth has been subject to the whims of cosmic forces beyond its control. Mass extinctions, climate changes, asteroid impacts. These were simply facts of existence that species had to endure or perish. But now, for the first time, a species has developed the knowledge to understand these cosmic processes and potentially the technology to influence them. We can detect incoming asteroids and comets. We can model climate systems and predict their behavior. We can even contemplate engineering projects on stellar scales. Whether Nemesis exists or not, the search for it has revealed something remarkable about human nature. Faced with the possibility of cosmic scale threats, we don't simply despair or deny the danger. We investigate, we plan, we develop technologies to fight back. This might be intelligence's ultimate purpose, not just to understand the universe, but to participate in shaping it, to transform from passive victims of cosmic forces to active agents of cosmic evolution. If Nemesis exists and approaches our solar system in the coming millennia, it will find Earth defended by a species that understands the threat and has prepared to meet it. If it doesn't exist, humanity will still have gained the knowledge and technology to protect itself against other cosmic dangers. Either way, the search for our dark companion has already changed us. We're no longer just another species waiting for extinction. We're cosmic engineers, capable of taking responsibility for our own survival and perhaps for the survival of all life on Earth. Darkness beyond our solar system may hide dangers we can barely imagine, but it also hides possibilities, new worlds to explore, new forms of life to discover, new challenges to overcome. Whether Nemesis exists or not, humanity's future lies not in hiding from cosmic forces, but in mastering them. And perhaps someday, in ensuring that the cosmic cycles of destruction and creation that shaped our evolution will continue to nurture intelligence and complexity throughout the galaxy, not as random catastrophes, but as carefully managed evolutionary pressures that help life reach its full potential among the stars. In the end, the search for Nemesis isn't just about finding a dark companion star. It's about discovering what we're capable of when faced with ultimate challenges. It's about becoming the kind of species that doesn't just survive extinction events, that learns to prevent them entirely. That might be our true cosmic destiny, not to be victims of stellar cycles, but to be their masters, to transform from a species shaped by cosmic catastrophes into a species that shapes cosmic evolution itself. Whether our dark companion exists or not, that journey has already begun.